Okay, so now let's see about the limits. First of all, what do you think should be the limit as uh, modulus of s tends to infinity of L of f of s? Okay, what should that be? Limit as s tends to infinity, integral 0 plus infinity, f of t e minus s t dt. Okay, so what do we get? So the thing is that you would like to be able to invert limit and integration, and can we do that? Well, yes, that would be the theorems on parameter dependent integral. We took actually the correct assumptions to say that e of minus of f of t was smaller in than some, let's say, some constant times e of at, so that that whole stuff would be smaller than e of minus s minus a times t, and we said that the convergence domain was real value of s greater than a. Okay, and in that case, well, it's going to be bounded above by some integrable functions, so we have no problem. You can use the usual parameter theorems on continuity of functions defined by parametric parameter dependent integral. Then you got that that's, for instance, continuity. That's an extension of continuity, actually. And you get that this is going to be the integral of the limit. And of course, the limit of this, as we assume that we had the correct majoration for f, that's going to be going to 0 as s tends to infinity. Okay, so that's always true. That limit is always 0. Okay, then we have this theorem, which is called theorem of initial and final values. Okay, so what is that saying? It says that the limit, first of all, the limit as z tends to 0 of s tends to 0, if I use the s variables of s, Laplace transform of some function of s is equal to the limit as t tends to infinity of your function of t. Okay, let's see what it has. If you see that, maybe that reminds you of the above formula that we obtained for the derivative. What we had was we had found that L of f prime was actually equal to s L of s minus f of 0. So what do we get? We get that this limit as s tends to 0, or sf of s, is equal to the limit as s tends to 0 of L of f prime of t of s plus f of 0. Okay, so let's write what we have. That's going to be the limit as s tends to 0 of the integral between 0 and plus infinity of f prime of t e minus st dt plus f of 0. And that is exactly what we said earlier. This, in any case, when the variable, this s tends, this s tends to 0, that's Oh, all right. Sorry. That's not what we said earlier, but this is what we'll get later on. Okay. When s tends to 0, well, I can exchange the integral and the limit. That's just giving me the integral between 0 and plus infinity of f prime of t dt plus f of 0, because the exponential of 0 is just 1. Okay, I've exchanged the limits and integration because, again, we took all the assumptions needed in order for that to work, and this is just exactly equal to the limit as t tends to infinity of f of t minus f of 0 plus f of 0. Okay, so this is our initial and final value theorem. Okay, the limit of s of L as s tends to 0 is the limit of the function at infinity. Okay, and if you saw that in the previous proof, actually we can if we had considered the limit as s tends to infinity of exactly the same thing as L of f of s, what do we get? What changes is that we would get here we would get infinity instead of 0, and so what do we have in that case? We would have that okay, so at infinity, when s tends to infinity, that's just going to give you, well, 0. Okay, because this is what we said earlier, that inner function goes to 0 as s tends to infinity, so the Laplace transform of anything goes to 0 as the variable of the Laplace variable tends to infinity. So that goes to 0, and we are only left with f of 0. Okay, excellent. So that's the second part of the initial and final value theorem. And finally, we have, well, more or less finally, we have to see the property concerning Laplace transform and convolution. If you remember, for instance, for the Fourier transform, the Fourier made convolution into product, and reversely, the made product into convolution. Okay, so let's see what we have here for the Laplace transform. So first of all, let's remind us what the convolution is. F convolved with G is going to be the integral on R of f of t minus s, well, I should maybe t minus x, g of x dx. Okay, but we said that both functions, now when we consider Laplace transform, we want both functions to be equal to 0, f and g. They are both equal to 0 on negative infinity 0, because, well, we should always consider them as being multiplied by these Heaviside function. So what do we get in that case? So that's going to be the integral on R of, let's write the whole stuff, of or plus of t minus x times f of t minus x times g, which is going to be integral on R plus, indicator on R plus of the x variable, g of x dx. Okay, so what do we need? We need x to be greater than 0, and we need t minus x to be greater than 0. So in the end, what do we get? We get that x should be between 0 and t. So in that case, this convolution is just then going to be rewritten as the integral between 0 and t, so f convolve with g of t as a function of t of f of t minus x g of x dx. Okay, so this being said, what do we then obtain for the Laplace transform of such a convolution? Okay, so actually it's not too hard to prove, so let's write that. That's going to be integral from 0 to plus infinity, so integral between 0 and t, f of t minus x, g of x dx, okay, times e minus st dt. Okay, so let's do a nice substitution. Let's put, I don't know, capital T is equal to T minus X. So that d t is going to be the small dt. So that's going to be integral from 0 to plus infinity, integral between 0 and small t, f of capital T, g of x dx, e minus s applied to t plus x. Okay, d capital T, and which I can rewrite as being integral 0 plus infinity integral 0 t. And I can put them separately together. So I've got oh, I forgot to take into account my bounds. So when the capital T was small t minus x, and as x goes from 0 to plus infinity, so now we have, no, sorry, when small t goes from 0 to plus infinity, we get that the small x should go from 0 to plus infinity if we rebound our bound. So that's, I'm sorry, that's a bit vague, but let's say that in the end we're going to get e minus st, and we're going to get g of x e minus sx dx dt. Okay, so that you can split them together, and we finally get that that's going to be the Laplace transform of f times the Laplace transform of g. Okay, Laplace transform of the convolution is the product of the Laplace transform. So what can we do? So again, we can do a lot of things with this. Maybe let's talk about the fact, a very important fact, is that the Laplace transform is invertible. So let's write this. So that we can use both properties to get some new formulas. Okay, so actually we can prove that, and it's well, it's a bit of a tedious calculation with complex functions. So as we haven't really worked with that, and we're not really going to work with that this year, I'm not going to do the details. But the Laplace transform is invertible, meaning that you have again what we expect, the good properties of a one-to-one correspondence, meaning if you know that, for instance, let's do some application. We knew that the Laplace transform of the Heaviside function was 1 over s, but then we also know that the inverse Laplace transform of 1 over s as a function of t is going to be the Heaviside function. Okay, so that's what it means. We have an isomorphism, if you like, even though I haven't clearly defined what spaces we were looking at. That's the point. The Laplace transform came earlier than all the others, and so its properties are less weren't created. They are very useful, but they weren't created to we didn't adapt the Lebesgue spaces to work with that, because actually the Fourier transform was way better for that. Okay, but however, it's invertible, meaning that if you have some Laplace transform, you can find back the original function. Example of application of that. I know that the Laplace transform of a convolution is going to be the product of the Laplace transforms, so that we get 1 over s squared. Okay, but what we've already seen, we've already saw some function that such that its Laplace transform was 1 over s squared. We have seen that earlier that the Laplace transform of t times h of t was also 1 over s squared as a function of s. As the Laplace transform is invertible or injective, well, that's the injection property that we're using, there is only one single preimage for the function 1 over s squared. So what we get is that the convolution of h with itself is actually equal to t times h. Okay, so that we didn't have to compute the convolution actually. Okay, so what would come next would be creating a table of usual Laplace transforms, and maybe that could be create a table of usual Laplace transforms, and maybe that's going to be the first exercise we can deal with in tutorial. Okay, good. Thank you. See you soon.